Welcome to G Fun Facts Online. In the vast, silent factories of the cosmos, where stars and planets are forged from colossal clouds of gas and dust, a grand mystery is unfolding. An elemental enigma, a cosmic vanishing act, has perplexed astronomers for decades. The element at the heart of this puzzle is sulfur. On Earth, you might associate it with the sharp smell of a struck match, or the pungent odor of volcanic vents. But in the grand scheme of the universe, sulfur is a VIP. It's the 10th most abundant element in the cosmos, and, crucially, a cornerstone of life as we know it. Yet, in the very places where the story of new worlds begins, the dense, frigid hearts of molecular clouds, it seems to disappear without a trace. This isn't a minor discrepancy. In some regions, up to 99.9% of the sulfur we expect to find is simply gone. This profound puzzle is known as the, quote, sulfur depletion problem, and it has launched a multi-decade scientific detective story. The quest to solve this cold case takes us from the unimaginably vast and cold expanse of interstellar space to the meticulous, controlled environments of laboratories here on Earth. Because finding the universe's missing sulfur isn't just about balancing a cosmic chemical budget. It's about tracing the journey of a life-giving element and probing the very origins of ourselves. Let's begin at the crime scene. For decades, astrochemists have faced this glaring discrepancy. When they point their powerful radio telescopes toward the diffuse interstellar clouds, those vast, wispy regions of gas and dust that litter the space between stars, they find sulfur in abundance, right where our models say it should be. In these low-density environments, where atoms are few and far between, sulfur exists mostly as a simple, singly ionized atom, which gives off a distinct radio frequency that our telescopes can easily pick up. It's a clean signal. But a strange transformation occurs as these clouds, over millions of years, begin to collapse under their own gravity. They contract and cool, becoming the dense, dark, and frigid molecular clouds that act as the universe's stellar nurseries. And it's here, in the cradle of creation, that the sulfur goes quiet. The strong, clear signal from the gas phase plummets, sometimes by a factor of 1,000. To put that in perspective, for every 1,000 sulfur atoms we expect to see floating in the gas, we can only find one. While other key elements for life, like carbon, nitrogen, and oxygen, also see their numbers drop as they freeze out onto dust grains, their depletion is nowhere near as dramatic. This begs the ultimate question: where did all the sulfur go? The leading hypothesis is that it hasn't vanished at all. It's just hiding. Scientists are convinced it's locked away on the surfaces of minuscule interstellar dust grains, incorporated into the thin mantles of ice that accumulate in these frigid environments. At temperatures hovering just 10 degrees above absolute zero, almost any gas phase atom or molecule that collides with a dust grain will stick, like frost on a window pane. Over eons, these grains build up icy layers of frozen water, carbon monoxide, carbon dioxide, and ammonia. The theory is that sulfur atoms get trapped in these ices too, and once there, they engage in a rich and complex surface chemistry, forming new molecules that are fiendishly difficult, if not impossible, to detect with our current astronomical techniques. These new icy sulfur compounds are the prime suspects in this cosmic disappearance. So if the bulk of the universe's missing sulfur is entombed in ice on a dust grain, what form does it take? This question has spurred a flurry of research, blending theoretical predictions with innovative lab experiments. The picture that's emerging is that sulfur is a chemical chameleon. It possesses a special ability known as catenation, which is a fancy term for its tendency to bond with itself to form long chains and stable rings. This unique property means the missing sulfur might not be locked up in simple molecules with other elements, but could have formed pure sulfur allotropes, molecules made only of sulfur atoms, hiding in plain sight. Recent work by astrochemists like Ryan Fortenberry and chemist Ralph Kaiser has spotlighted two particularly stable and therefore likely candidates for these hidden reservoirs. The first is a fascinating molecule called octasulfur, or S. In this molecule, 8 sulfur atoms link together to form a distinctive, crown-shaped ring. This is the most stable form of sulfur at standard conditions here on Earth, and sophisticated models predict it could be a major component of the frozen sulfur inventory out in deep space. The second group of molecules are polysulfanes, which are chains of sulfur atoms with a hydrogen atom capping each end. The reason these molecules have eluded us for so long is that they are locked in a solid, icy matrix. They aren't freely rotating in the gas phase, so they don't produce the sharp, clean, spectral lines that radio telescopes are so good at detecting. They are essentially dark to our conventional methods of astronomical observation, forcing us to find new ways to hunt for them. To crack the case, scientists have to become cosmic forensic investigators, and their lab is right here on Earth. In highly sophisticated vacuum chambers, they painstakingly recreate the extreme conditions of interstellar space. They start with a tiny, cryogenically cooled surface, chilled to just a few Kelvin, colder than anywhere in our solar system. Onto this surface, they deposit thin layers of molecules like water, carbon monoxide, and various simple sulfur-containing compounds, building up an artificial interstellar ice mantle, molecule by molecule. Then, to simulate the harsh radiation environment of a dense cloud, they bombard these artificial dust grains with electrons or ultraviolet photons, mimicking the effects of cosmic rays in background starlight. These experiments provide an unprecedented window into the chemical factory of an ice grain. Using techniques like infrared spectroscopy, which detects the unique vibrations of molecules, scientists can track the formation and destruction of compounds in real time. For instance, experiments have shown that processing ices containing hydrogen sulfide, a simple sulfur-bearing molecule believed to be a key starting point, can kickstart a whole network of reactions. Highly reactive fragments are created, which can then combine with other ingredients in the ice to form more complex species like ethanethiol. Other lab simulations, starting with different ingredients like sulfur dioxide, have shown that a complex, interconnected web of reactions can convert simple sulfur carriers into a diverse range of products. The incredible breakthrough from this research is the realization that the missing sulfur is likely distributed across a whole family of complex molecules and polymers, not just one or two simple species. And crucially, this lab work provides the final piece of the puzzle for astronomers: the spectral data, the unique light signatures of these molecules. It's like creating a most wanted poster with a clear mugshot, telling astronomers exactly what to look for when they point their most powerful telescopes at the sky. And there is no telescope more powerful right now than the James Webb Space Telescope. While the laboratories provide the mugshots of our potential sulfur culprits, it's up to telescopes to find them in the wild. For decades, this has been a deeply frustrating search, but the successful deployment of JWST has, in the words of many astronomers, been a complete game changer. With its gigantic golden mirror, unprecedented sensitivity, and powerful suite of infrared instruments, JWST is peeling back the layers of the cosmos like never before. Its primary method for analyzing the chemical makeup of distant objects is spectroscopy. By capturing the light from a star that has passed through the atmosphere of an orbiting exoplanet or the dusty veil of a stellar nursery, astronomers can see which specific wavelengths of light have been absorbed. Each molecule absorbs light at a unique set of characteristic wavelengths, creating a, quote, chemical fingerprint or spectrum that reveals its presence and abundance. One of JWST's most stunning early results was the first ever detection of sulfur dioxide in the atmosphere of an exoplanet. The target was WASP-39b, a hot Saturn, located about 700 light-years away. The discovery was monumental, not just because it found a sulfur molecule, but because of what its presence implies. The chemical models of WASP-39b's atmosphere predicted that sulfur dioxide should be there in such quantities on its own. Its existence can only be explained by photochemistry, a continuous process of chemical reactions triggered by the high-energy ultraviolet light from the planet's host star. The theory is that the starlight rips apart water molecules, creating highly reactive fragments that then attack the main sulfur source, likely hydrogen sulfide, to produce the observed sulfur dioxide. This was the first time a photochemical byproduct had been definitively detected on an exoplanet, opening up a whole new field of study into the active, dynamic chemistry of alien atmospheres. JWST's sulfur hunt has not stopped there. It has found sulfur dioxide in the atmosphere of another exoplanet, the hot Neptune GJ3470b, making it the lightest and coldest exoplanet known to host the molecule. In another fascinating case, observations of the potentially rocky super-Earth L 98-59d suggest an atmosphere rich in sulfur compounds like hydrogen sulfide and sulfur dioxide. The stench of burnt matches and rotten eggs on a distant world might sound unpleasant, but to an astrobiologist, it could be a tantalizing hint of active volcanism on the planet's surface, a geological process that is crucial for cycling nutrients and maintaining a long-term habitable environment. Now, it's important to note that JWST cannot directly see the S-rings or polysulfane chains predicted to be hiding in the coldest, densest ices. But its ability to detect molecules like sulfur dioxide is a critical piece of the puzzle. It confirms that sulfur is present and is actively participating in chemical reactions in a variety of environments. The next step is to look at regions where stars are just beginning to heat up their surroundings. As these ices warm and sublimate, turning directly from a solid into a gas, they will release their hidden contents. Armed with the spectral data from laboratory studies, astronomers will use JWST to search for the telltale fingerprints of these more complex sulfur molecules, finally solving the mystery of the missing sulfur. The early results are just the beginning, transforming the hunt from a frustrating search into a thrilling mission of discovery. This brings us back to the ultimate why. The quest to find the universe's missing sulfur is not driven by mere cosmic bookkeeping. It is deeply connected to one of the most profound questions in science: how did life begin? Sulfur is one of the 6 CHNOPS elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, that are absolutely essential for life on Earth. Its role is ancient and fundamental, woven into the very fabric of our biochemistry. Sulfur's biological indispensability is most evident in its presence within 2 of the 20 standard amino acids, methionine and cysteine. These amino acids are the critical building blocks of proteins, the molecular machines that carry out the vast majority of functions within a cell. The sulfur atoms in these molecules often form disulfide bonds, which act like tiny structural staples, helping proteins to fold into their correct 3-dimensional shapes, a shape that is absolutely essential for their function. If a protein misfolds, it can't do its job, which can have catastrophic consequences for an organism. Beyond this structural role, sulfur is also a key component of vital molecules like the vitamins thiamine and biotin, and coenzyme A, an essential player in cellular metabolism that helps us synthesize fats, proteins, and carbohydrates. This connection between sulfur and life likely stretches back to Earth's earliest history, long before oxygen filled our atmosphere. Life is thought to have emerged in anoxic environments, perhaps around deep-sea hydrothermal vents gushing with sulfur-rich minerals. Early life forms are believed to have harnessed energy from chemical reactions involving sulfur and iron, with some scientists proposing that the very first systems for capturing and utilizing energy were simple iron-sulfur clusters. This deep connection makes the study of cosmic sulfur particularly compelling. The theory of panspermia, in its broadest sense, suggests that the raw materials for life, the complex organic molecules needed to get things started, were not necessarily synthesized on the primordial Earth. Instead, they were delivered here by a constant bombardment of comets and asteroids. These icy bodies are pristine time capsules, remnants from the formation of the solar system, preserving a chemical snapshot of the molecular cloud from which our sun and planets were born. Recent laboratory experiments have provided tantalizing evidence for this scenario. By simulating the conditions of interstellar ices, scientists have demonstrated that complex sulfur-containing organic molecules, like alkyl sulfonic acids, can form abiotically in space. These molecules are water-soluble and could have provided an accessible source of sulfur for the first organisms on a young, watery Earth. Other lab work has shown how reactions in these ices can lead to the formation of other complex molecules, including ethanethiol. These experiments confirm that the icy dust grains in interstellar space are veritable factories for producing the kinds of complex molecules needed for life. Therefore, the hunt for sulfur in icy space dust is, in a very real sense, a hunt for our own origins. By identifying the full inventory of sulfur-bearing molecules in the interstellar medium, astronomers and astrochemists are piecing together the starter kit for life that was available in our solar system 4.5 billion years ago. Did the ices that formed the Earth and rained down upon it contain simple sulfur hydrides or more complex organosulfur molecules? Did they contain the very amino acids, like cysteine and methionine, that are now central to our biology? By tracking sulfur from its disappearance in dense clouds to its potential hiding places in icy dust and its re-emergence in the atmospheres of new worlds, we are tracing the cosmic pathway of a life-giving element. Each discovery brings us closer to understanding whether the ingredients for life are a common cosmic inheritance, scattered like seeds throughout the galaxy, just waiting for the right conditions to take root. The case of the missing sulfur is far from closed, but for the first time, we have the tools, the theories, and the talent to finally solve it.